Hello everyone, and welcome to today's webinar on the characterization and failure analysis of optoelectronic materials and devices. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time. Dr. Udit Sharma, Project Manager at EAG, will be answering some of the questions during the presentation. We will also collect these questions and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Dr. Michael Salmon, Scientific Fellow of the Advanced Imaging Group at EAG Laboratories.
Hi, good morning, good afternoon, and good evening, depending on where you are in the world. This is an exciting platform to give talks on. Glad to see so many people could make it today. So as Rena said, my name is Mike Salmon. I'm the Scientific Fellow for the Advanced Imaging Group, and I'm based in the Raleigh, North Carolina lab. I got my PhD in Material Science and Engineering from North Carolina State University under Dr. Phil Russell, and with an emphasis on microscopy and surface analysis. And I graduated in 2006 and joined EAG in January or February of 2007. And while here at EAG, I've had a career that's focused on highly localized characterization and failure analysis of compound semiconductors. So now just a brief introduction to EAG itself. All the dots here on the global map indicate an EAG laboratory. As you may see, we have a presence in over 20 locations, covering 4 continents, staffed with over 600 highly educated and experienced scientists. We serve over 4,000 different clients per year who are located in 50 countries. So for today's webinar, I'm going to go over a little background really briefly here, just to talk about optoelectronics principles, some common devices, and talk about the EAG Smart Chart, which you might already know about. It used to be called the bubble chart. And then we'll go into the characterization and failure analysis, looking at some common opto failure mechanisms, developing a common strategy for FA, as well as some of the common characterization techniques required for root cause determination. And then intertwined within that, I'll be going over some FA and materials characterization examples to try to show how we can use these techniques to successfully figure out what's going wrong. And then a brief summary. So optoelectronics in general the word itself is formed from opto, which comes from Greek, meaning visible or pertaining to light, and electronics, which are devices that deal with the emission, flow, and control of electrons. So optoelectronics are electronic devices that then create, detect, and control light. And these are based on different quantum mechanical effects of light on electronic materials, especially semiconductors. And here on the right are some of these quantum mechanical effects and the associated different devices that utilize them. So some examples of common optoelectronic devices that you probably know about. You've got LEDs and lasers, photodetectors, and solar cells. Most of these devices utilize compound semiconductor materials that are combinations of elements from group 3 and group 5, like GaN, gas, or indium phosphide, or group 2 with group 6 elements like cadmium telluride, zinc selenide, and zinc oxide. Compound semiconductors have advantageous physical properties such as direct band gaps and higher power densities relative to their elemental semiconductors such as silicon or germanium that are really what enable modern efficient optoelectronic devices. So this is the EAG Smart Chart, and this chart shows all the techniques available at EAG, quite a few here. We call it the Smart Chart because it stands for Spectroscopy and Microscopy Analytical Resolution Tool. The vertical axis here of the chart here show the detection range, and this represents the concentration detection limits in atoms per cubic centimeter and atomic percent. And the bottom axis here represents the analytical spot size range. The colors of each of these circles represent the type of information that are extracted from the technique, such as the blue techniques give elemental information and the orange provide molecular information. And these are described in the bottom left legend. The techniques outside the chart are pure imaging techniques, which don't contain concentration information, or bulk techniques over here, which have no spatial resolution effectively. You can find an interactive version of this chart at this website here, www.eag.com/techniques. And I recommend you go check it out. You can mouse over each of these different techniques, and then you can dive further in depth to information about each one of these things. And that can oftentimes be very useful to steer you sort of in the right direction for the type of analysis you may need. So for this talk today, though, we're going to focus primarily on light and electron microscopy techniques that are most commonly utilized for a compound semiconductor FA. But certainly other techniques like dynamic SIMs or something like that, if you need to look at the minority properties of your material like dopants, et cetera, you really need a technique like SIMs to really get at those very low concentration materials. So with that, we need to think a little bit about what are some of the common opto failure mechanisms. And semiconductor lasers and LEDs have an extremely tough job with carrier recombination rates thousands of times higher than other types of devices. They've been made quite reliable by careful design and screening, but aren't inherently reliable. There are two main types of failure. You have wear out and maverick. Wear out failure is typically a gradual type of failure. It's a part that fails due to something that's consumed until it can no longer do its job properly. Whereas maverick failures are typically abrupt and have some sort of defect incorporated into them, with much worse lifetimes than others from the same batch, and fall well outside the 95% confidence limits for the bulk of the population. So really understanding whether a failure is due to wear out or maverick is really one of the most important questions for FA analysts. And typically it's the maverick failures that are going to then become the primary source of interest for most products. So in trying to understand the failure, one of the biggest challenges you're going to face is locating the actual defect site, as optoelectronic devices can have quite large emission areas or optical cavities, and the defects can be as small as a few nanometers in diameter. Often there's no visible sign of their presence from the surface of the device, so only degradation of light output or changes in IV character provide evidence of their presence. Ideally, the device is also going to be at least partially operational and hasn't suffered catastrophic failure, as it's nearly impossible to identify the source of failure if large-scale destruction of the sample has occurred. High current densities and large thermal gradients drive defect growth and often lead to catastrophic failure very rapidly. So any reliability experiments must be run with extra special care to catch failures as early as possible. And this is obviously easier said than done in many cases. So with this in mind, we like to develop a successful FA strategy as we look at it. And so we sort of divide the tasks up into three different levels. So you have a level 1 tasks, which we consider routine characterization techniques. These are going to include non-destructive techniques like optical or light current voltage assessment, as well as potentially electroluminescence imaging. And these are things that are going to get done all the time on every device, every failure. And then from that information that we get from that first set of data, some samples or some will be interesting enough that where we really want to look a little bit closer and do some intermediate failure localization. So this is level 2 type work. This is something where we're going to be able to hopefully isolate the failure to within let's say, a quarter of a micron resolution. So we're going to utilize techniques such as optical beam induced resistance change. So this is a scanning laser technique called Oberch, as well as electron beam induced current, which is an SEM technique. And we're only going to do this on specific failures that maybe are unusual or we don't quite understand from the level 1 characterization. And then from there, there'll be another subset of samples that need further understanding. And so we call this level 3 or deep FA. And this is where we head into destructive analysis. So we're going to use focus ion beam, dual beam, to cut into the sample and image with SEM to try to understand how the defect is propagating through the epitaxy, et cetera. And then we're going to use scanning transmission electron microscopy, in some cases maybe cathode luminescence or CL, to really try to get at root cause determination for these specific failures. And so as we try to keep this in mind, this is sort of a slide showing the subset of microscopy techniques we can utilize here for these 3 different levels. So the optical microscopy gets us to about 1 micron to, in some cases, a quarter of a micron resolution in the case of Oberch, et cetera. And then we can then extend that down into scanning microscopy techniques, SEM, SEM-EBIC if we want some elemental analysis, EBIC, cathode luminescence. And then that takes us further. That takes us down. I mean, the spatial resolutions of SEM are down on the order of 1 nanometer now. So that gives us very high resolution in most cases, but it doesn't really give us much information about the crystallography in the sample, which oftentimes the defects that are causing the degradation are crystalline in nature. And so that means that we need to do more destructive types of analysis where we have to do fib lift out and TEM of those materials to try to understand what's going on with the crystallography. And that gets us down to the ability, in the case of spherical aberration corrected stem or AC stem, we now have sub-angstrom resolutions for that kind of imaging. So the sort of the idea is finding the needle in the haystack, and so we're going to utilize techniques that have lower spatial resolutions initially, and we're going to dig down and essentially try to hone in on the location of that defect using these different techniques to ultimately take the picture in the end that's going to really let us understand how and why the device failed. So for the purposes of this talk, we'll be using a commercially available high brightness LED that we here at EAG purchased and then intentionally overstressed to failure. Typically, we are provided similar failed or failing parts by our clients, but since we're rarely allowed to share our clients' data, we've had to create our own failed device to show you how we can then apply the variety of analytical techniques to help better understand the root cause of failure. So in this case, we take this common LED, we do some IV characteristics tests before showing that we have good diode behavior. We actually remove this protective diode here and then apply a large reverse bias at high current to kill the device, and then we find that we have a shorted device that has ohmic behavior after the test. A really good resource for more information about this particular analysis that we're going over, it can be found at this website here, and this just goes into talking about all the different types of analysis we can perform on this. It's called LED analysis. You can search eag.com for LED analysis and you'll get to it pretty quick. And that goes over a wide variety of different techniques, even some more packaging level stuff, which I'm not going over in this talk as much. And so this takes us to sort of level 1 routine characterization on the sample. So we'll do some optical inspection first. And then if it's highly embedded like it was, we need to verify the issue is due to the semiconductor and not the other passive components. So we've done that, and then we've, to confirm it's a device issue, we extract the device. So over here is a picture of the de-encapsulated die, still with the bond wires intact, if possible. And so then we're going to collect IV data over the entire operating conditions for the device. We're going to, in this case, lower light output is occurred. We actually have no light output anymore. And So how much degradation really does give you clues to potential root causes and allows you to then create sort of a feedback loop within the different levels of analysis you're doing. So, and then in a lot of cases, we can use electroluminescence imaging on devices that are still at least partially functional to directly map like where the light is being quenched, for instance, here. But in this case, we have a short, right? So after the stress test, we know we have this ohmic behavior now. So we don't really have a partially functional device. So for doing intermediate defect localization, if we did have a partially functional device, we would probably try something like SEM or electroluminescence imaging to try to hone in on where the defect is. But since we know we have a shorted device in this case, we're going to use this scanning laser technique, or OBERCH, to give us our first indications of where in this millimeter square die the defect is. And so OBERCH stands for optical beam induced resistance change. In this case, we're going to be using a laser that's generating electron hole pairs through excitation above the band gap. And this is particularly a good technique for locating shorts. There's another mode called TIVA, where we're then looking at the voltage change by rastering a laser. In this case, it's typically below the band gap, and then we're only looking at changes in the voltage due to heating in the sample alone. So in this case, we're using this OBERCH situation, and we get this mapping of the resistance change across the sample itself, and we see that we have this very distinctive low point here where the resistance falls. And this corresponds to this location here if we overlay it on the optical image. And so then we can now we have a place to look over the entire, look more closely. So out of this, millimeter square area, now we've got this much smaller region that we can hone in on using SEM, for instance. And so SEM stands for scanning electron microscopy. In this case, we're going to use a focused probe of electrons, not light as in the case of the scanning laser. We can vary the energy of the electrons from about 500 volts up to 30 kV in most cases in our systems. And then the interaction of this primary electron beam with the sample generates all kinds of useful signals that we can have different detectors for. And so we can collect this data at the same time. So secondary electrons are typically utilized to give not topographical information about the sample, but at the same time, we can collect electron beam induced current signal and then correspond that to the secondary electron image. So we have good fiducial reference for that. Or we can collect X-rays or Auger electrons or backscatter electrons, etc. So ultimately, we're going to acquire these images in a serial acquisition. So this enables us to collect them at each different point as we go. And another thing is that this SEM is much more useful in some ways, as it gives a greater depth of focus than the optical microscope. And so you get more of a 3D quality, and it helps you really understand a little bit better where things are happening. And so now if we use the SEM, we know where to look on the sample from the OBERCH. We can then zoom in right here on this location, and we can see that we have a significant meltdown site. So it looks like the sample in some ways maybe chipped out, like that the sample's broken, and then also evidence of melting and resolidification in this location. And so then we can proceed now to level 3, where we're going to initially start with dual beam cross-sectioning. So in the case of dual beam, now we're combining a gallium focused ion beam with an electron beam at a given angle to the two. And so we can use the focused ion beam to actually deposit. We can use the electron beam to deposit material at first as well to protect the surface, then the ion beam to add a little bit more, a capping layer. And then we can use the ion beam itself to remove materials, physically sputter material out of the sample. So then we can see more clearly in cross-section how this defect evolves through the epitaxy. And in this case, you can see the pattern sapphire substrate. This is the GAN buffer region, and then the active layers are up here near the surface. And so from this, we can really see that we have like a large meltdown. So what we sort of assess from the surface, and you can see that it extends, a micron or so into the sample. And in this case, though, maybe it'd be very helpful to get more information about the crystallography within the sample, which we can't get from SEM. So we need to further proceed to TEM and try to examine the epi a bit further. So in this case, what we can do is we can use the fib again to remove material from the backside of this cross section back here. We can physically remove that, we can undercut that, and then actually lift this out in situ using a nano manipulator in the dual beam itself, and put it on a TM grid and then put it into the stem. And so this is an example now of looking through a thin section that we've removed. So we've thinned this lift out cross section. It's probably 150 nanometers thick or so. And so this gives us now an idea of what's going on within the crystal itself. So in the bright field mode, we can really see the evolution of a lot of threading dislocations up through the epitaxy. And then we can really look at and see the extent of how this defect is formed within the device. And so if we look at a region here, this is a STEM Z contrast image, so high angle annular dark field image, which shows us really nice the different compositions of layers in the structure itself. You've got the InGaN multi-quantum well region here, and then you've got a InGaN superlattice, some AlGaN electron blocking layer, and your PGaN cap up here. And so then there's some other layers as well, like your surface dielectric and the ITO P contact over here. And you can really see that the entire defect sort of spans across the junction, which you would expect. So it looks like, you know, effectively you had a short occur, and then all the current flow through this region, which then led to the meltdown. So ultimately, in this case, the biggest problem we're having is that the actual destruction of the sample or the creating this failure, we didn't catch it early enough. So it was allowed to go on long enough to where the sample really consumed the defect that caused the issue to begin with. So we kind of have to circle back a little bit here to try to understand this a little bit better. So we want to go back to maybe our level 2 techniques and maybe look at devices that haven't been pushed to failure yet to try to understand this. So maybe let's try EBIC on a known good sample and see if we can find any interesting features with EBIC that might lend themselves to being these kinds of very localized sites that would be prone to failure. So in the case of electron beam induced current, or EBIC, we're going to use the SEM beam to inject carriers into our semiconductor that has a PN junction, and we're going to raster that electron beam across the surface. This technique can be done in either SEM or STEM as well. And effectively what we're going to do is we're going to map the electric field strength in the sample. And typically the maximum is at the PN junction, and electrically active defects in the sample are going to reduce that and appear as dark spots or dark regions where you're having localized recombination. And then ultimately you can do it in plan view, so where the beam is normal to the junction, or you can also do this in cross section where you're rastering the beam across the junction. Ultimately, cross-sectional EBIC, you're going to want samples that are typically cleaved, but we can also do focused ion beam cross-sectioning as well and have good experience creating low damage, low implanted cross-sections to still be able to do EBIC. Ultimately, the resolution is going to be mainly determined by the interaction volume that I showed before, which is then related to the accelerating voltage in the SEM. And it's also a bit related to the minority carrier diffusion length of the material itself. So materials like gallium arsenide will have slightly different ultimate resolutions than, say, gallium nitride. So here's an example of us using SEM-EBIC on a known good LED, and we can scan obviously the entire this entire chip very quickly. And what we see is that the signal itself is actually very sensitive to changes in thickness. So areas that have thick metal on the surface, we're really reducing the amount of electrons and holes we can inject near the junction itself. So those appear very dark. You also see different residues from the actual decapping or deprocessing of the LED itself. But we do see that we find some other interesting geometric looking contrasts here that further should be looked at further. Some things to remember about the limitations of doing EBIC are really you're only giving access to a small portion of the active region when you do cross-sectioning, so you really need to know where to put that cross-section. And as I mentioned, even small amounts of topography can become a big issue. So if you have a very rough surface, you're going to have very different thicknesses of the material above the active layer. This can be a really big problem to try to actually discern where a defect might be versus just a change in topography. Things like semiconductor laser ridges can often have thick metals, which can prevent the injection of carriers. So we have a lot of expertise at actually stripping thick gold layers like that to remove that. Or in some cases, we can do fib work to gain access to the active layers. Thick devices such as VCSELs and other devices don't really often work that well in plan view, just because the current injection is limited by the kV. So you've got a couple of microns probably of depth that you can actively inject. And so like with VCSELs, you've got many microns often of mirror layers there above the active layers. But we can use the focused ion beam in some cases to gain access. You also really need to have ohmic contact, so you need a functional device. It needs to be partially functional still so that we can collect the EBIC signal and that there isn't such a large, let's say, current shunt that where that EBIC signal could travel outside of the detection scheme. So if you don't have ohmic contacts or you're interested in more sort of research design kind of stuff, we can also try SEM-CL as well to look at defects and how they propagate through crystals. But in the case of this talk today, I just don't really have the time to go into that in a whole lot of depth, but you're more than welcome to contact me if you have questions regarding that. So like I said, we should look a little bit closer at this type of defect that we're seeing here, this signature in EBIC. And if we do zoom in on it, we actually see that we have this very bright spot with like a dark ring around it. And it's got some hexagonal quality to it actually. So it looks like there's some crystallography involved, which is very interesting. And then we have this very bright spot just to the right of that. There is some indication of this feature in the secondary electron image here on the right. And it looks like there may be a pit here, like so there's a little dark spot that maybe corresponds to this bright spot here. So what we've done and what we can do is we mark this cross-section location very carefully in the SEM, and then we use the dual beam to lift it out in situ and image this in the scanning transmission electron microscope. So now you're seeing in cross-section that same location across the defect, and we identify that there's sort of three main features here. We see that there's a quantum well disruption up here near the surface. There's this vertical feature here, as well as we can actually see a pit in the ITO over here to the right. So for this vertical feature, we can actually identify this now as a nanopipe in the structure. And in our dedicated STEMs here in North Carolina, we have secondary electron detectors where we can actually look at the surfaces of the foil. And so you can actually see this bright up, which is a signature of a void or a hole. And so in this case, we've got a nanopipe that spans a large portion of this cross section. So you got to remember this cross section itself is about 150 nanometers thick. So it's actually, you can see it leaving the foil down here, and it extends up through the foil and then leaves here again. But this feature itself is actually centered on this quantum well disruption. And so if we can then take this STEM data and using and correspond it to the EBIC data we have now. And so we can actually look and see how this EBIC data relates to what's going on in the sample. And so if we take this region here in the red box and stretch it in the Y direction, sort of we can exacerbate what's going on in these thinner layers, and we can really see this massive multi-quantum well disruption that's occurring here. And so now we can really understand why the EBIC signal is brighter in the center. It's because our active layers are actually closer to the surface than on either side of it. And in fact, it's darker on either side because they end up being further away here and then heading back towards the surface again. So now the EBIC signature really makes sense. And then what's of really big interest is actually this pit here, right? So we have a pit in the ITO, and you can actually see that the ITO extends down almost now into the multi-quantum well. And this is where our electrical junction is. So we actually have this very sharp V defect type pit. It's got conductive material that actually gets down further into the sample. And so this is a really good candidate, or a highly likely site of where, if you're reverse biasing this device with significant energy, you could get breakdown to occur and potentially diffusion of this material down and cause the short in the device at this location. So using SEM-EBIC, we actually then, we get a little further insight into why we got such catastrophic failure in the case of our stress test on our other LED. So defects like this then become very interesting. So what is it about this particular defect? In this case, it's two dislocations that come together that form this V pit. So something about it disrupts. Obviously, the nanopipe is causing disruption and growth, and you get this quantum well disruption. So the crystal itself is growing in different rates because of the experience or the environment around this particular defect. But the same thing is true about this dislocation sort of annihilation of this combination of two defects here to the right. So in a lot of cases, we need to then use STEM to look at defect analysis. So how can we sort out the different types of threading defects? So are they screw, or are they edge, or are they mixed, for instance? And so we like to use STEM for this task versus just conventional TM bright field, because the STEM bright field images show much more simplified and uniform contrast than the TEM. So in the TM, you've got some thickness fringes and bend contours. This is the exact same sample imaged in TEM and STEM here, and you can just see how much simpler the contrast is in the STEM, and how nice the background versus the defect is, right? So it really makes it easy. They stand out well, and we can look at these defects in both cross-section or plan view, right? So we can see how in a cross-section how these defects evolve from the substrate up into the surface into the active layers. But we can also then, in some cases, if we're interested in understanding the defect densities themselves, it's probably more statistically relevant to look at these things in plan view. So we can, using the fib, we can target very specific depths in the sample to create plan views. Here, this number 1 is at the near the interface with the substrate, so the buffer region. Number 2 is then at the mid growth of the GAN, and then number 3 is just in the active layers themselves. And so we can create different plan views at these different depths to then understand the evolution of the defects in terms of defect density going up through the sample. But not only that, like I mentioned, we want to understand more about the type of dislocation that they are. So using some crystallography, we can then take 3 images, one on zone, and then one at different reflection vectors, one for the A direction, one for C. And in the case of the A direction, this gives us the edge character of the defects. And then in this reflection vector, this gives us the screw character. So then we can then tabulate effectively all the different types of defects within the sample, within this cross section. And actually notice here, this defect is missing from the edge tilt, whereas it appears here in the screw tilt. So we can actually identify this particular defect as screw only. And this is the opposite for the defect here. It's missing in the screw, but it's present in the edge. So we know that this is a pure edge defect here. Whereas the majority of the defects are actually mixed. They appear in both tilt situations. And so it becomes important to then try to understand how how these populations of screw and edge and mixed maybe vary between different samples, or in the case of defects that cause the issue, if we still have them present in the sample, we can then understand something more about how to potentially get rid of them by studying this. So in a lot of cases, it's not just defects that are maybe controlling the issue. It could also be layer compositions or even interface abruptness that becomes really important. And so the next technique that we have to dig further down is aberration corrected STEM, so AC STEM. So the idea behind AC STEM is that effectively the objective lens in the STEM is going to have spherical aberration issues, and so the further away from the optical axis that electrons get in the column, this lens, the aberrations cause over focusing, and then eventually our final probe will be blurred somewhat because of this aberration. So to optimize it in the past, we've had to use an aperture which effectively cuts off these off-axis electrons, which effectively lowers our probe current. So that makes things a little bit more difficult to get the signal and noise that you need. But so ultimately what we do in the case of aberration corrected STEM is we add a corrector which adds in the negative spherical aberration coefficients of the objective lens, allowing us to focus even the off-axis electrons to a very fine spot. So the ultimate takeaway is we get a smaller probe with larger probe current. So this really enables another level of discretion as far as spatial resolution and signal to noise for analytical work, both imaging and for things like EDS and EELs, which I'm not really getting into a lot here, but are definitely techniques that are of interest more on the materials characterization side. So this is an example of how we can use aberration corrected STEM to look at the interfaces within LED structure, multi-quantum well, in-GaN quantum well like this. So this is the substrate side on the left, and this is the surface side here on the right. And just, qualitatively, you might be able to just see that it appears the substrate side looks a little bit more abrupt than the surface side. And if we take an average line profile through this red box here, you can actually see we can quantitatively measure this kind of change now with atomic precision. So on the substrate side, you can see as the indium turns on, you get this really nice abrupt step up, and as you grow this layer and then turn the indium off, you get a much more gradual change in composition. So either the indium is purposely being turned off slowly, or there's a resonance time for indium in the system. But it's this kind of discretion now that gives us the ability to really look in more detail and potentially quantify from sample to sample the differences that are there, that then you can correlate to your optical properties, for instance, or the device performance. So really moving on now, how are we going to really extract the most information from our AC STEM images? And effectively within these Z contrast AC STEM images, there's a wealth of chemical and structural information available, and so we can get composition information through the intensity from the columns themselves. We can actually also get things like strain and distortion and structural uniformity based on column shape. Things like the lattice parameter and nanometer scale lattice distortions and phase changes should also be available. And so really, how can we do this? And effectively, what we can do is we can use computational image analysis to help us quantify these differences. And so, and this is an example of LMSO or PZT, strain PZT on LMSO material. And so we can actually use some software to find the centers of every atomic column here in the crystal, and then we can color code them relative to their average value for lattice spacing in the C-axis. And then if we take an average line profile here, we can plot this, and then you can see here's LMSO on the left. Typically it's 3.8 angstroms, so we can see how that value sort of targets right around that. And then at the interface, we can actually see that there's a region of strain PZT that then relaxes back towards the known bulk PZT value. So we can actually perform this kind of quantitative analysis from sample to sample and have a way to really accurately compare samples over time. And you can also plot sort of more globally the data into histograms, et cetera. So there's different ways you can actually visualize this. You can also measure the out of plane strain as well, and things like that. Certainly there are issues with sample relaxation and things that must be taken into account, but ultimately through careful controls, you should be able to set up a situation where you can really measure this kind of feature over time and get some valuable information out of it. So with that, I'm going to summarize the talk today and just say that EAG has we're very highly experienced in optoelectronics characterization and FA of compound semiconductor devices. Myself, I've been working for almost 15 years doing this here in North Carolina. We have currently have a wide range of instrumentation techniques and characterization expertise that's required for the successful localization of device altering defects. We can perform very highly targeted sample prep with very low damage using focused ion beam. We can then characterize the nature of defects in the stem or with CL, for instance, and really use all these techniques to then help determine the root cause of failure. We're also committed to the continuous improvement and development of instrumentation techniques and expertise required to satisfy our clients' needs. So why would you choose EAG? I just want to complete this webinar with this one final note. There are several reasons, but I think it's important to state right at the top that client confidentiality is core to our business, and we are in full realization of the sensitivity of working with proprietary products and have in-house built security systems to protect confidential information. We're a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. We're continuously building our instrumental capabilities to meet our clients' needs. And lastly, in light of the pandemic that's affecting all of us right now, I just want to stress that EAG Labs is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID-19 regulations from state and local governments as well as CDC. Currently, all of our locations throughout the world remain open, but we may have limitations on customer visits, of course. And this is certainly a fluid situation where we're operating a laboratory at reduced capacity, but we can transfer your samples to other locations if needed. It's really not a problem. We encourage you, of course, to discuss your options with your sales representatives.